Hello everyone, we are here for session 20. So in session 20 I'm going to cover two topics: combining forecasts and time series decomposition. So combining forecasts is chapter 5 appendix in your textbook on page number 278. So in first part of video we'll go through that and come back to time series decomposition. So here's the brief agenda. So we'll go through some introduction to combining forecast, things that you need to keep in mind, and then we'll move on to the regression process to determine right weights when it comes to combining different models. In terms of learning objectives, so you will be assessed on explaining the process, how to go about combining two or more forecasts, and then you should be able to apply the regression process. So I have some questions uploaded to Top Hat, as well as you have a worksheet, so please work through that. If you have any questions, reach me out. Okay, so let's kick off with some terms and the importance. So what we mean by combining forecasts? So the idea here is to use forecasts generated for a time series using different models, such as Winter's model or curves, and combining those forecasts using some weight so that we can generate a final forecast which is combination of two different models. So that's the idea behind combining forecasts. The next question is why we combine. So there's lots of empirical evidence from research literature, from the publications, that combining forecasts outperforms the single model. So in order to understand this, let's go back to our healthcare data. Number of new patients registered with a healthcare facility. So what we did in that data set, we use a simple method, moving averages, where we're not looking into any external factors or seasonal patterns. We treat time series as stationary, very simple model. Then we use Winter's method. We were able to deal with seasonality. Forecast was improved than the moving average method. Then we went beyond that. We used causal regression model. So in causal regression model, we dealt with seasonality using dummy variables, and we added few more variables such as time index, and then we had the population, FTE, full-time equivalent productivity. So as we were adding more and more variables, what was happening, we're looking into the relationship aspect between those variables. So the idea here is we always focus on improving some measure of accuracy, such as MAPE or root mean square error. So when you are focusing on improving MAPE, we either remove some variables, add new variables, or use a different model. And that model is only tested for certain data set, and it's only true for that data set. The relationships only hold for that data set. So when we go beyond or out of sample, your model may not perform same. Part of the reason, because we may have missed some relationships. There may be some other important variables which are not dealt by the model you have selected in the forecasting process. So by combining, we are combining different models which are looking at data from a different perspective. So before we go to regression process to determine the weights, let's look into the biased. If all of your individual errors are positive, or 3 consecutive or more errors are positive or negative, we can say your model is biased. So one of the assumptions that we have here is that your model is not biased. So we're going to check for bias by using statistical analysis. What would happen if you use a model which is biased? Any biased model you're going to use in combining forecast is going to make your forecast worse. That's why your model shouldn't be biased. In a perfect situation, we can use some models which are negatively correlated. So if you pick up two models, take the correlation between errors. If it's negatively correlated, means for one model over predicting, and for one model we are under predicting. So if you combine those two models, we can improve the forecasting accuracy. So most of the bias, it comes from preconceived notions or the beliefs a particular individual have. So most of the biases are from the individual who is involved in the analytics or the demand planning process, because he's using certain types of tools or forecasting methods. It always favors for those methods. So one of the things you must keep in mind when we're checking for bias, a model is said to be unbiased if it has an intercept of 0 and slope of 1. you are going to get a 0 forecast error, right? But in real life, that's not going to happen. So in real life, you're going to get the models where either the intercept is negative or the intercept is positive, which means either you are over predicting or you're under predicting. So the next question is, how are we going to check if the intercept is statistically significant or not? So that's why we're going to use the regression process and doing the t-test, right? So we'll walk through that process. I will highly recommend, please have a look at these 3 slides so that you're aware of what we mean by bias forecast. This is kind of very generic process, so where you have different forecasts being produced. So what we're doing here is we are assigning weight with respect to each forecast. So for instance, W1 is for forecasting method 1, which is judgmental method, W2 for method 2, 3 for forecast 3, and W4 for forecast 4. So that brings us to a very important topic, which is choosing weights. A very simple method is that you give equal weight. So for instance, we have 4 forecasts which are produced using different methods. So if I'm using equal weights, so we're going to have 0.25 as a weight assigned to all the forecasts. All these weights, W1, W2, W3 and W4, must add up to 1. Well, now you can see, I mean, this method is not good. So ideally you want to assign more weights to the forecasts which are better than the others, right? So one of the measures you can use for that is looking into MAPE values. Lower the MAPE value, higher the weight. What the weights must add up to 1. So before we start regression analysis, one quick note. In the regression analysis, our final forecast is a modified regression equation, and in this regression equation we have no intercept. So intercept A is equals to 0 for our final forecast equation. So remember from the earlier topic we went through on bias. So a forecast is said to be unbiased if you plot actual and forecasted values and it passes through a region. So we're going to keep this assumption in our mind as we walk through the process. Okay, so let's walk through the regression process. So in this regression process, we are writing a simple equation for multiple regression where you have actual values, which is y, equals to intercept, which is A, slope, B1, or the weight for first forecasting model, and F1 is the forecast value for model 1. So in our example, we're going to use Winter's model as F1, or our first forecasting method, and causal regression as our second forecasting method, F2. Okay, so let's work through a real data file. So you have a file which is provided through Blackboard. It's called session 20 combined forecast. This file we have actual sales, so this is Y. Then you have interest prediction, F1, which is these values are obtained from forecast X. F2 are coming from multiple regression model, right? Okay, so let's use Excel data analysis tool pack to get the intercept and slope values. So I'm going to go to data, then data analysis, then from here we're going to look into regression, and I have input which is in column B for Y range, and input range for X, Winter's prediction and regression prediction. So I'm selecting from A1 to D25. Yes, we have labels, and let's produce the results here. Okay, so I'm just going to put the slide and Excel document side by side. So actual equals to intercept, which is A. So here's the intercept, here's the coefficient for intercept. So I'm going to highlight this, and then the next question is, okay, this coefficient is 145, it is not 0, right? Is it statistically significant or not? So we're going to check statistical significance of this intercept value. We're going to do t-test for it. So statistical significance will allow you to check if there's a bias between different models. means between Winters model and F2, which is multiple regression model. So if the models are unbiased, intercept A should not be statistically significant. So how we perform t-test, just a quick reminder. We set the hypothesis. So null hypothesis is going to be intercept is equals to 0, and H1 or alternative hypothesis is not equals to 0. So for two-tailed test, we're going to get t critical value. So you're going to get this value on 95% confidence level. So as I said, if the confidence level is not given, you always use 95%. So alpha over 2, so which means 0.05 over 2. The alpha over 2 is going to be 0.025. The most common mistake I have seen in exam and in real life when it comes to degrees of freedom. The degrees of a multiple causal regression model are always equals to n minus k plus 1. N are number of observations, k are number of independent variables. So in this case we have 2 independent variables, and I believe there are 24 observations. You can check that in Excel document. In this case, our degrees of freedom are equals to 21, not 3. Okay, so we got t critical. I believe it comes around 2.78, something like that, where you can check that value for the exact number. And then we get t calculated. So I'm going to go back to Excel again. So we have t calculated here for the intercept term, so which is 0.289. So once you got t calculated, then we're going to make a decision, right? So reject null hypothesis if t calculated is greater than t critical. In our case, our t calculated is 0.289 and t critical is 2.70, something like that. So in which case we fail to reject null hypothesis. So when you fail to reject null hypothesis, means the intercept is equals to 0. The intercept value in this case, which is 145.42, is not statistically significant. Okay, so the alternative way to check this is you can look into p-value. But from the exam viewpoint, you should know both methods using t-stat and as well as p-value. So in this case, the p-value is 0.77, and which is greater than alpha or significance level 0.05. So which means H naught stands true, or the null hypothesis is true. So we fail to reject null hypothesis, which means intercept is equals to 0. So from here we can conclude that Winters model and causal regression method are not biased. Hence, we can combine these two methods. Okay, so up to this point, we have only tested for the intercept term. So what the next question is, how are we going to get the slope values? Remember, we looked at the bias part. So we said when the models are unbiased, it's going to pass through the origin. So we're going to do the regression again, and at this time, we're going to force our intercept to be 0. Okay, so let's look into this. So I'm going to go back to the Excel document again. Let's rename this sheet. I'm going to say this as intercept t-test. So let's go back to the original data set and data analysis, regression. So I have my y input range from B1 to B25, X input range from C1 to D25. Most important part, when you're determining the weights, constant is 0. So when you check that, it's going to force the regression line to pass through the origin, right? So which means your models are not biased. Let's press OK. So we have our intercept 0. We have forced the line to pass through the origin. So for the Winters model, we have the slope as 0.743, and for regression model we have a slope as 0.258. So if we add these two, so I'm going to take sum of these two values, and you will see it's approximately equals to 1, right? That's what you're expecting after combining all the coefficients. Are these coefficients statistically significant? Answer to that is yes. Both of these values are greater than 1.96, right? You can look into p-value. So I'm going to change this to number quickly so that it makes more sense. So 0 is less than 0.05, statistically significant, yes. Less than 0.05, yes, right? So just in case these values are not less than 0.05, that means your slope is not statistically significant. Then sometimes it's a call where the individual needs to use his experience to see if combining two models are going to create a greater value or not. Well, from the statistical analysis viewpoint, you can look into p-value and t-stat. So that's about the weights. Okay, so before we go ahead with this, let's go back to Excel sheet. So for your reference, I have 2.04 mean absolute percentage error for the winter's prediction and 4.04 for the regression prediction. And what we did here, we got the slope, right? So 0.743. I want to write here slope 0.743, and the slope for second model is 0.258. So now we can produce final forecast. So what was our final forecast? So here's our final forecast, which is B1 F1. So I got my slope value for winter's model 0.743 and for a regression model 0.258, right? So we are going to have our final model is going to this equation from here, right? Because we have only two methods. If you have three methods, you're going to have B3, F3, and so on, right? So let's put these values in and let's see what MAPE value we are getting here. So I'm going to combine these two forecasts. Equals 0.743 multiplied by winter's prediction, which is C2, plus 0.258 multiplied by regression prediction, which is D2. So that's my final forecast for period 1 or for Feb 2010. And if you apply that across, so we got our forecast for first 24 periods up to November 2015. And from here we can calculate absolute percentage error, which is absolute value of actual, which is B2, minus forecast, which is E2, divided by the actual, 1.18%. And let's scroll this down, apply across all the cells, and now we can calculate MAPE, the combined forecast model, which is coming as 1.69. And even from this statistical viewpoint, the MAPE value for the winter's prediction is 2.04, and we have higher weight allocated to the forecast which has a lower MAPE value. Here 4.04, the weight is 0.258. So overall your model is improved. It's better prediction than predicting individually through those models. So this concludes combining forecasts process. So there's some important considerations. Have a look at that. So rely on t ratios or t value. If a slope is not statistically different from 0, then it's not going to produce better results. So that's why I said even for the slope values, after forcing your line to pass through 0, always check the weight for the slope terms. If it's not statistically significant, it's not wise to move forward with this. It's not going to produce a better forecast. If slope is negative, discard that forecast from the final combination. I just want to highlight one more point because I'm not sure if I have mentioned that earlier or not. Okay, so as I said earlier, please go through top hat questions, work through worksheet. If you have any questions, reach me out. Thank you.